Hello students. Okay, so in the last lecture I told you that now we are going to deal with more realistic problems, and in order to study the real problem we'll try to study metals and solids, and in order to study that we have to include the interaction of the electron with the positive ion cores. Okay, so now, and also I told you all that the electron in the solids, they experience periodic potential. Okay, and also I mentioned that there was a physicist known as Bloch who said that whenever the potential is periodic, the wave function has a special form. Okay, so let us try to see again. Okay, so we are going to study electron in periodic potential. Okay, and what kind of potential it is? The potential has an infinite row of rectangular potential wells separated by barrier of width b. And this I have explained in the last lecture. How is it? Okay, so let me take the barrier minus b, 0 and a. Okay, let me take this as region 1 and this is region 2, and this unit from here to here, it repeats again and again, and the potential height I take v0. The electron is approaching with energy E, which is less than v0. Okay, this is my electron, so I'm taking this case. And who approximated, simplified this model? Kronig and Penney. So we also call this as Kronig Penney model, and there was a very deep inside physics which came out from this model. We'll see. Okay, so now how do I solve this problem? I write the Schrödinger equation for region 1 and 2 for an electron moving in the lattice. Okay, the Schrödinger equation for an electron moving in the lattice is given by in region 1. For example, if I take from 0, x is equal to 0 to a, there is the potential is 0. So what equation do I get? d2 psi 1 by dx square plus 2m upon h cross square e psi 1 is equal to 0. Okay, 0 to a, and 2me upon h cross square I can take as k1 square. This is region 1. Now in region 2, d2 psi 2 upon dx square minus 2m upon h cross square. This we have already seen in the tunneling problem in the rectangular potential barrier, and this comes out to be v0 minus e psi 2 is equal to 0. This is for x minus b to 0. Okay, and I can take 2m v0 minus e upon h cross square is equal to k2 square. Okay, now I've already discussed that my potential in the solid is periodic. So when the potential is periodic, the wave functions have a special form. But first let me write the solutions for psi 1 and psi 2. Okay, so let me call this as equation 1, this is as equation 2. Now for equation 1, the solution is the solution of the equation one and 2 are psi 1x is equal to a e to power I k1x plus b e to power minus I k1x. Okay, 3. K1 already I have defined 2me upon h cross square, k1 square. Psi 2x is equal to c e to power k2x plus d e to power minus k2x. Okay, these are exponentially decaying solution. Question number 4. Now Bloch suggested, already we have proved. Okay, so here I would be using the result now. Bloch suggested that for a potential which is periodic, Vx is equal to Vx plus a the wave function should be of the form psi of x is equal to ukx e to the power ikx. Please don't get confused with this k with k1 and k2. These are related to the energies. Okay, and here, so this is my k1 square is 2me upon h cross square. K2 square is 2m v0 minus e upon h cross square. Here k is an index to label the solution. K is a index to label the solution, and also this ukx, it has the periodicity of the lattice. Okay, okay, these are known as Bloch wave function. Now my solution must be Bloch functions. Okay, now if I substitute this wave function in the Schrödinger equation, what do I get? This is equation number 5. I get d2u upon dx square plus 2ik du by dx plus k1 square minus k square. This you can easily check by substituting your wave function u of x is equal to 0. This is understood when x is 0 to a, and d2u, so basically it is u1. Okay, u2 dx square plus 2ik du by dx minus k2 square plus k square u is equal to 0, and x is minus b to 0. Okay, the solution of these equations would be the same exponential and the exponentially decaying, exponential, the oscillatory, and the exponentially decaying solutions. So my equation number was 5, so these are 6 and 7. 6 and 7. Okay, the solution is u1 is equal to a e to power I k1 minus k x plus b e to power minus I k1 plus k into x. Okay, one can check that, just straightforward. u2 would be c e to the power, now this is exponentially decaying and growing, k2 minus ik x plus d e to power minus k2 plus ik x when x is minus b to 0. Okay, and a, b, c, d are the constants. Now what we have to do, we have to just substitute as we have done in the earlier problems of step potential and rectangular potential. We have to apply the boundary conditions. What are the boundary conditions? That at x is equal to 0, the wave functions and their derivatives are continuous, and also we will apply that wave functions are periodic. So now applying the boundary conditions so these are my equation number 8 and 9. What are my boundary conditions? u1 at x is equal to 0 is equal to u2 at x is equal to 0, and its derivatives du1 by dx at x is equal to 0 is equal to 0. Okay, so these are the wave function and the derivatives are continuous, and u1 at a is equal to u1 at minus b. This is my wave functions are periodic. du1 by dx at x is equal to a is equal to du2 by dx at x is equal to minus b. These are my periodic wave functions conditions, and these are the wave functions and the derivatives are continuous. By applying these conditions, 4 equations, we will get 4 equations in with constants a, b, c and d. Now the 4 equations, okay, here I will leave few mathematical steps, okay, which you all can solve. The 4 equations to have a solution exactly in the similar way what we did in tunneling. Okay, then we'll try to, here I would like to focus more about the physics of the solution. Okay, so I'm not going the detail, I leave it as an exercise for the students. Okay, this is an exercise. So what you have to do, you have to just apply all these 4 boundary conditions in the 4 equations which we have here in the solutions 8 and 9. We get 4 equations, and these 4 equations to have a solution only if the determinant of the coefficient vanishes. The 4 equations to have a solution only if the determinant of the coefficient vanishes. If I do that, what do I get? k2 square minus k1 square upon 2 k1 k2, okay, sine hyperbolic h hyperbolic k2b sine k1a plus cos hyperbolic k2b cos k1a. Okay, these are k1, k2, k1, k2. K1 is a momenta in which the potential is 0. So my k1 is 2 me upon h cross square. K2 is the in where is a measure of energy when there is a potential v naught. So 2m v naught minus E upon h cross square. This is equal to cos k. K is the index to label the solution, A plus B. So when you put the determinant 0, you will get this equation. Okay. Now, so what is my equation number? 8, 9. Then these are my boundary conditions, A and B. Okay. By solving all these boundary conditions in 8 and 9, I will get this equation. Okay, this is very straightforward. I will leave it as exercise. Now, this result is simplified if we represent the potential by the limit. What was my actual potential? If I go back here, what do? If this potential, the width of the well B goes to 0, and the potential V naught goes to infinite. In such a way, so what do we get that? Basically, it's a Dirac delta function. Yes. So basically, what do? The area under the curve remains same. We want to see in this limit, and this solution is simplified. So what Kronig and Penney suggested, what to do here? The result is simplified. The result is simplified if we represent the potential by a limit. Okay, that is my actual real limit. That, because in the beginning we have estimated as it as an infinite row of rectangular potential barriers. Now I'm putting back the limit that the width of the well, it goes to 0, and the height of the barrier goes to infinity, in such a way that the product of the width and the height is finite. By a limit, B tends to 0 and V naught tends to infinity, in such a way that V naught into B remains finite. Okay. Now this we have to see. What equation do I get when I do this? Okay. So I have to use this limit. B tends to 0, V naught tends to infinity, and V naught be finite. Once again, I'll remind you, this is a very important limit, and I'll show you that our solution which we got, it reduces to what? Here, k1 square, once again I'll remind you, is 2me upon h cross square, and k2 square is 2m v naught minus E upon h cross square. Okay. So now try to see the equation number 10 in detail. Okay. How that equation transfer in a very simple form by applying this limit. Okay. So we'll try to see. So maybe what I do, I divide my screen into 3 parts. Okay. Because in this equation I have first part, first term, second term, and let me take as third term. Left hand side has 2 terms and the right hand side has 1 term. So let me, the first term is big, so I give bigger space to that. Let me see whether I will be able to complete in this or not. Okay. So this is left hand side, first term, left hand side, second term, right hand side, third term. Okay. Here we have a equal, here we have plus. Fine. Now let me first tell you the easy part. Now here, right hand side, it is cos k a plus b. I don't have v naught. Okay. So I have only b, and b tends to 0. So what do I get in the right hand side? So I can just simply put b is equal to 0. So right hand side I will get cos k a. Okay, this is a simple result. Now I would like to do left hand side second term. It has two cos hyperbolic k2b and cos k1a. Cos k1a is constant. Okay, k1 is 2me upon h cross square, k1 square. Energy is constant, so everything is constant, nothing to worry. So cos k1a is same. Only term remaining is cos hyperbolic k2b. Let us try to see that. Okay, it has cos hyperbolic k2b and cos k1a. This remains constant. Now what is k2? k2 is equal to under root 2m v naught minus e. Now when v naught tends to infinity, it is very large compared to e. So I can neglect e because v naught is greater than e. This upon h cross square. Fine. Now in this, if I multiply, I want to take v naught out. Okay. So sorry, I have k2b. Here k2b. So I will take b also here. Now I will take root m root v naught. I will multiply root v naught in numerator and denominator. H cross square root v naught. Fine. This will become root 2m v naught b upon h cross square root v naught. Now from the limit, v naught b is finite. Okay, and v naught tends to infinity. When v naught tends to infinity, this term will become very, very small. So when v naught tends to infinity, k2b tends to 0. And you all know that cos hyperbolic k2b is equal to, can be expressed, cos hyperbolic k2b can be expressed as exponential k2b plus exponential minus k2b upon 2. When k2b tends to 0, this is 1 plus 1 upon 2 and this goes to 1. Clear? So now cos hyperbolic k2b tends to 1 in this limit. So only term remaining in this is cos k1a. So this term we get finally the answer as cos k1a. Now what is remaining? Okay, here we get cos ka, we get cos ka. Here we get, okay, there is less space, so I am making it bit small, cos k1a. Fine. Now we come back to the first term. It is bit big. It has 3 terms. Sin k1a, that remains constant. Sin hyperbolic k2b, here k2 we has v naught b, here also k2. Okay, so we'll see. I'll just copy this term here. What do I get? k2 square minus k1 square upon 2 k1 k2 sin hyperbolic k2b sin k1a. Okay, now what do I get in this term? Okay, now here you see that in the first term we have already seen k2b. Here k2b tends to 0. Okay, so here also k2b tends to 0, this whole tends to 0, but we see here that there is another term which is k2 square which has v naught, so it is increasing. So this is going to 0, but this is going to infinity, so the increase may offset the decrease, so we cannot put this equal to 0. So what limit we have to take? That sine hyperbolic k to b, it goes to 0. So we can expand this in the small k to b. K to b can be written as e to the power k to b minus e to power minus k to b upon 2. K to p is very small, so I can expand that. The expansion of e to power x is 1 plus x square, so on. Higher order terms will be 0 because k to b is very small. So I can keep only the first order term. So 1 plus k to b minus 1 minus k to b upon 2. K to b is very small, so what do I get? Here minus 1 plus we get approximately k to b. Okay, so sine hyperbolic k to b is approximated as k to b. Now term left is first one. K2 is very greater than k1, so I can neglect k1 square. I get k2 square minus k1 upon 2 k1 k2 is equal to k2 square upon 2 k1 k2. K2 will cancel. I will get k2 upon 2 k1. Fine. So by writing all these three terms together, what do I get? Okay, sorry, this is k2. K2 upon 2 k1. I'll just clean this, otherwise there will be a confusion. My rubber. So I'll just, okay, and here also this is k2. Fine. Okay, k2 upon 2 k1 into k2b from sine hyperbolic k to b into sine k1a. Okay, now I can multiply and divide with a in numerator and denominator. Fine. What I will get? K2 square ab. Okay, so this is equal to k2 square ab sine k1a upon 2 k1a upon 2 k1a. Fine. And k2 square I can write 2m v0 upon h cross square. I can again neglect e with respect to v0. Okay, if I substitute that, I want to do in the same page. Okay, k2 square, if I substitute 2m v0 ab sine k1a upon h cross square 2 k1a. 2 will cancel. What do I get? m v0 ab upon h cross square. Okay, this I write as a constant p. So what do I get here? P sine k1a upon k1a. This is my simplified expression in this limit when b tends to 0 and v0 tends to infinity, such that v0b remains finite. Now I write the full equation again. My equation number 10. Okay, what was my equation? Once again I write for you. K2 square minus K1 square upon 2 K1 K2 sine hyperbolic K2b sine K1a plus cos hyperbolic K2b cos K1a is equal to cos K a plus b. This equation number 10 in the limit b tends to 0, v0 tends to infinity in such a way that v0b remains finite. Okay, in this limit, this equation reduces to a very simple form, that is p sine k1a upon k1a plus cos k1a is equal to cos k, where this I have just shown to you all, where p is m v0 ab upon h cross square. There is a very important point to note here. P contains v0 into b, and that represents the barrier strength. Okay, v0 b is finite, barrier strength. Okay, this is a very beautiful simple equation, and we can understand a lot of physics from this equation. So you see, the left hand side is a function of k1a, okay, and right hand side is an index, k is an index to label the solution. Okay, I'll stop here, and in the next lecture we will try to see the beautiful physics which comes out from this equation. Okay, thank you.